Hello everyone, and welcome back to the series on Introduction to MATLAB Programming. Today we're going to be looking at some of the basics associated to image processing, in particular basic color analysis for images. So the first thing that we need to do is import an image into our MATLAB programming environment. So in order to do that, all you need is an image, for example in PNG or JPG format, and then we need to bring that into the environment, and typically you can just click and drag that into the current live folder of your MATLAB program. Once you do so, then we need to import that image into our MATLAB environment. So in order to do that, we just use, or first we need to define what we're actually going to call our image. So we're going to be storing our image in the object A, and in order to read in that image into the MATLAB world, because in order to calculate things, we need to first define what that object actually is. So we're going to just be using the mread command, and then we're going to be using the exact file name dot the same exact extension as your file is. So the file that I'm going to be using is called QDog.jpg, and you'll see why I'm using that name in just a moment. But QDog.jpg is going to be the file name that my actual image is named. Keep in mind, if you capitalize any letters in your actual name, it has to be capitalized here, so this is indeed case sensitive. The second thing I want to figure out is to find the resolution. So we're going to extract the resolution of this image. Now, most images are going to be colored images. That means the matrix, in some sense, is going to be a tier 3 matrix. It's going to have rows, columns, and in addition, 3 different layers corresponding to the red, green, and blue spectrums of your computer image. So we're going to store the number of rows in M, the number of columns in N, and the third dimension is always going to be 3 for colored images, so I'm not going to store that into any particular variable, but if you want to store it in, say, Z or something like that, you can, for example, do so, but you have to have something there when you return the size of this particular 3-tier matrix, A. All right, so once you have that, then we can display our image. So we're going to display it in, for example, figure 1, and we're going to display that image using the image function. So our image is stored in object A, and it's going to show some axes by default. If you want to show those axes in your image, feel free to do so, but I'm going to remove them. And then we're going to give this image a title. So we're going to display the actual image name and the resolution inside of our title. So what we're going to do, and since we're going to have some numerics converted to strings in the title, we're going to put brackets here. And this is going to be the original image. And then the size is going to be equal to, then first is going to come the number of rows by the number of columns, which is going to be equal to m. All right, so once you have all of that typed out, all we have to do is just give this function a run, and you will see that this is our image, and that is the cute dog. At least I think so. Right? And it says original image, and then the size is equal to a 747 by 747 by 3 colored image, right? And that is the image that I'm going to be working with, and you probably have your own image, and that's perfectly fine, and you can, for example, do all of the things that I'm doing, provided that you have the image processing toolbox. Most of the MATLAB base packages do not have it. So all you need to do is just download the image processing toolbox, and you'll have some of these functions, or you can try to code them yourself. I'm using the basic MATLAB programming tools, for example, for loops, and also your plots. Should be able to do these on your own, as long as you have the basic programming skills to do so. Now, the next thing that I want to do is analyze the color distributions of the red, green, and blue spectrums for this particular image. So the first thing that I need to do is extract the actual color layers in this image. So we're going to acquire the color layers in our image, layers of our image. So the first layer is going to be red. So we want all rows, all columns, the first layer, that's going to be red. And then age is going to be the green layer, so that's all rows, all columns, and the second layer, which is going to be green. And then AB is going to be, again, all rows, all columns, and the third layer, which is going to be the blue layer. You could do a subset of the image, for example, the first 10 columns and the first 10 rows, or any combination thereof, and you can just change those columns to the dimensions that you want. But I want the whole entire red, green, and blue layer of my colored image, and that's going to give them to me. Now I want to display those images just to sort of see what's going on within each of those color domains. So the second figure is going to show all of the layers, and we're going to show them all in grayscale. And in just a moment, we'll actually show you how to do different color distributions or color bars for each of the color layers of your image. But for now, we're just going to show them all in grayscale. That's just a basic way to show them. So we're going to be showing them in the same exact figure, in particular one row by 3 column subplot. So 1 row, 3 column, and the first element is going to be the red layer. So we're going to image the image AR. Again, we're going to axis off, and then we're going to color bar this. So let's color bar this. That's going to show the color bar on the right hand side. And let's do a color map of, for example, gray. And there are other default color bars in MatLab, but gray is one of the basic ones. And the first picture is going to be the red layer. So this is going to be for image AR. Now for subplots, you cannot, at least by default, do different color maps for subplot images. This color map is going to apply to all 3 images, and it's going to take priority, and you can figure out, for example, if you do 3 different color maps on the 3 different subplots, which one will take priority. I'll let you explore that on your own in case you're interested, but there can only be by default 1 color map for a subplot approach, which is why later we're going to show them in 3 different images with 3 different color maps there. So that's going to be our first subplot. So our second subplot, again, we're going to be doing in the same 1 by 3 array, and then the second index is going to be associated to the green spectrum. Again, axis off. The color bar and the color map are still going to be associated, so we do not need to necessarily include them. But the color bar I want to include, but the color map's still by default going to be the gray one. So we're going to title this the green layer. And then the last one, so subplot, first row, third column, third index of that sequence, is going to be the blue sequence. So again, axis off, and then we'll color bar that, and then we'll display the title blue layer. And that's going to show each of the layers, red, green, and blue in the grayscale spectrum. So this is going to be our image, and let's sort of spread that out and see sort of what's going on there. So those are our different layers. Now, how do you interpret this? And when we look at them individually in different color maps, this is actually going to make a lot more sense. So 0 in the first image corresponds to no red at all. Complete white means that the red spectrum is almost maximal at that particular pixel. For example, on Cute Dog's head, the red spectrum is really, really strong there. And on her little cheek there by her nose, that's also strong red. Now, if we go over to the green color, everywhere there's a black, for example, on her nose, that means there is little to no green strength for that particular pixel, and where it's extremely white, for example, where that bright grass is, that's where practically the green is almost optimal there. And then when we look at the blue, 0 corresponds to practically no blue in that particular pixel. And where you see almost white, that means it's almost optimal there in terms of the blue strength. So for example, if you look at the nose, we have practically a sort of bluish tint there. So it's sort of like an average of blue and green there. And you can analyze, for example, the average of red and green, the average of green and blue, and the average of red and blue, and sort of see what those look like, and even maybe the average of all 3 of them, or any linear combination thereof, and you can analyze that. So what I want to go ahead and do is actually look at each of these layers individually with their own spectrums of red, green, and blue, and also show you how to create your own color maps just in case you're interested in being a little bit more artistic with your displays. What I've gone ahead and done is I've pretty much outlined where we're going to fill in some of our new code, which is going to allow us to create three separate images for our red, green, and blue color layers, with, of course, the axis off. You can switch it on if you want. And we're also going to have a color bar. So if we actually go ahead and run this, it's actually going to create three different images, one for the blue, one for the green, and one for the red. And it's going to, by default, put them in a grayscale scheme. But what this would be actually really useful is to, for example, do a discretization of the 0 to 255 color spectrum, maybe in 5 subpartitions, and also do, for example, the red layer in spectrums of red, the green in, say, some subpartitions in, of the spectrum of green, and for example 5 subpartitions of the spectrum of blue, and that will sort of give us a more intuitive understanding of the strength of red, the strength of blue, and the strength of green for a particular set of pixels within some given range. And of course you can change these ranges. I'm going to do 0 to 25, 25 to 50, 50 to 75, and 75 to 100% in terms of the color sets that this is going to sort of partition our color images in. But you can choose your own segmentation partitions for the color spectrums depending on your interest, and you do not have to just do 5 sets. You can do more than 5 sets if you want a more smoother color transition, but of course the less you have, the easier it is to partition or segment your image into red subpartitions. So in order to create your own color map, so what we need to do is we need to create a several row by 3 column matrix. Those 3 columns are going to correspond to the red, green, and blue values on a continuous spectrum from 0 to 1. The first row is going to correspond to the first layer, which we're going to default to be black, which is going to be 0, 0, 0. The second layer is going to be the second color that you want to color on your color bar. So I want to be slightly red, so 0, 0.25, 0, 0, so that's a little dark red, closer to black. And then if I do 0.500, that's a little bit more of a brighter red. And then 0.7500, that's even more of a brighter red. And 100, that's the brightest red spectrum that you can have. And of course, make sure you put this as a matrix with brackets on the left and the right, columns separating, commas preferably separating your columns, and semicolons separating your rows. So that's going to be our color bar for our red spectrum, and you don't have to do these colors, but it's usually more useful if you do this in ascending order. For example, 0.1, 2, 3, 4, 5, 6, 7, 8, 9, and 1 would be a reasonable sequence with 11 partitions if you want it to be. I'm going to do a similar sequence for our green layer. For example, RGB, that's no green at R. RGB, that's a little dark green. And RGMB, that's a little brighter green. Then RGMB, that's brighter green, and then RGMB, that's the brightest green color in the computer spectrum, isolated from the red and blue spectrums, of course. And then I'm going to do a similar sequence for the blue layer as well. So I'm going to do, again, RGMB, so black would correspond to no blue at R. RGMB, again, that's going to be our darker navy blue, and then RGMB, that's going to be our middle tier shade of blue, and then we're going to have our R, G, and B. That's going to be a brighter blue, but not too bright. And then R, G, and B. That's going to be the brightest blue in the color spectrum that we have in isolation of the red and green. So that's how you can create your own color maps with as many colors as you want. So you can really be artistic and colorful as long as it doesn't hurt your or others' eyes, of course. So if we give this a run, that's going to actually go ahead and create our images, provided that I do not have any errors in this code. And of course I forgot one small thing. It should say color map and not just color. So let's just change that right quick and everything should work out fine and smoothly. So once I give that a run, now we're going to have our different colors here. There's our blue cute dog, our green cute dog, and our red cute dog. So everywhere you see this bright red color, for example, on the cheek, to the left of the nose, on the belly, and to the right, and a couple places in the grass, that's where the red has a very strong color, somewhere around 210 to 255 intensity level in the red spectrum. Over here in the green, wherever you see that bright green color, for example, in the grass there on the left hand side of the cheek, on the nose, and a lot more on the chest there compared to the red spectrum where it's sort of partitioned there, we have a lot more green intensity. And then in the blue spectrum, everywhere you see that really, really bright blue, that's where the blue is really intense. And everywhere you see black, there's practically no black at all. Blue in particular, what I mean to say is blue, right? But everywhere you can see the grass. So the grass is practically dominant in the green spectrum. The grass has a little bit of a red shade to it, but the grass doesn't appear to have any blue shade to it. And when you get into, for example, image identification and image segmentation, a little bit more advanced techniques, those little identifiers is going to be very, very useful in order to identify particular objects or regions in your image. Although up to this point we are able to analyze the red, green, and blue spectrums of our image, and we can partition that into as many subcategories from 0 to 255 as we want, perhaps we would like to look at the overall distribution of the intensities of this image in a more statistical manner. So one of the more better ways to analyze the color distributions in MATLAB or general for any language for image processing is to use histograms. So let's create some color layer histograms for the grid, green, and blue image. So what I'm going to do is I'm going to create one figure, and we're going to show all three histograms in the same exact subplot, sort of like we did before for our grayscaled versions of our color layer intensity distributions. So what we're going to do is, again, we're going to do a 1x3 grid, and the first is going to be mhist of the AR, the red layer of our image. And keep in mind, generally speaking, depending on the model of MATLAB you're working with, mhist probably will not work unless you have the image processing toolbox already installed. But this is going to be the red layer histogram. We're going to do the same thing for the second cell, so first row, third column, second index. So mhist AG, and this is going to be the green layer histogram. So green layer histogram, and then the second, or the third maybe, 1, 3, and index 3 is going to be mhist of A, R, G, and B. And this is going to be the blue layer histogram. So that's going to create the three histograms, and we can sort of see, should we treat the green with the same intensity as the blue? Should we treat maybe the red a little bit more sensitive when we're trying to identify objects? These histograms are going to help us answer some of those questions. So once we give this entire program a run, we're going to have our cute little histogram distribution shown here. So let's just sort of enlarge that to sort of analyze this a little bit more closer. So if we look at the distributions, for example, of red and green, notice that we have one plateau, two plateau, three plateaus for the red distribution. For the green layer distribution, notice we have one plateau, and for the blue layer distribution, we have 1 and 2 plateaus. If you know anything about, for example, distribution comparison test, for example, the Kolmogorov-Smirnov test for probability distribution comparisons from intermediate statistics, then you probably want to, answer questions. Is there a significant difference between the distributions of red and green, red and blue, green and blue, or any other different types of color distribution layers that you are trying to analyze here? But at least here we have pretty much almost a skewed right distribution for the red layer, heavily skewed right distribution for the blue layer, and almost like a almost normal but slightly skewed right normal distribution for the green layer as well. So based upon that information and whatever type of distributions you are looking at for your distribution, if you want to sort of analyze the red, green, and blue layer, if you come up to the conclusion that red and green have a similar distribution, you can create, for example, an equally weighted for red and green transformation if you want to. But for the blue, if you see that blue is significantly different from green and red, then you might have to treat that color distribution a little bit more sensitively different or just omit it completely if you desire. One of the applications that you might want to use this histogram analysis for the color layer distributions of a particular colored image for is grayscale transformations. So if the distributions of red, green, and blue are practically the same, you probably want to weight all of the red, green, and blue layers evenly, in particular a third, a third, and a third, or 33% approximately for each of those distributions. So what I want to do is convert my colored image to grayscaled images. So convert to grayscale images. So I'm actually going to do it two different ways. One is going to be the naive way. So if you believe that the distributions for red, green, and blue are practically the same, then we're going to be weighting them differently. So of course this is not going to be an isomorphic transformation. Once you convert it to grayscale, you cannot necessarily convert back to the original without knowing something a little bit extra about your image. That is, it's not a one-to-one transformation. So if we weight each of them individually, then we're going to do, for example, 33% of the red layer plus 33% of the green layer, and then 33% of the blue layer. Now notice I've done 0.334 instead of 0.333. The sum of those weights should be equal to 1, and I'm just treating that one a little bit more higher because the distribution is slightly a little bit more different. Of course, I'm hand-waving these observations a little bit, but this is in the scenario where they're practically the same, where B is slightly different than the G and the R distributions. Now another distribution that some people actually just default to is the standard RGB to gray transformation that is already pre-built into MATLAB, which is just going to convert that m by n by 3 matrix into an m by n via a distribution scaling that is already pre-calculated in MATLAB, which is actually equal to 0.299 times AR plus 0.587 times AG plus 0.114 times AB. Now, if you're not sure why or where these numbers come from, that's a fun little possibly probability exercise you might want to do. Just take a bunch of random images and average them out and try and figure out sort of where these numbers should come from and why these images are actually defaulted in this particular program, at least in this particular version of MATLAB anyway. So what I want to do is I want to actually compare these grayscale images. They're both going to be grayscale images, but they're going to be slightly different to each other. So what I want to do is I want to put them next to each other, and if you just have two images and you want to compare them, there's a function that's called mShowPair that actually allows you to do so quite easily. So the first image is going to be GA1, and GA2 is going to be the second, and if you want to put them on top of each other, just press that and that will do so. But if you want to put them next to each other, you need to tell it to make a montage out of those pictures. Let's give this a nice little title. So this is going to be the grayscale transformations of our image, right? And it looks like that parenthesis should not be there. Right? And the next thing I want to actually look at is, well, is there really a significant difference between them? So the next thing I want to do is look at the difference between those matrices, right? Because they're m by n matrices, so I should be able to just subtract them quite easily. So I'm going to mShow the absolute difference between them, so GA1 minus GA2 of that. And then I'm going to color map that. And then the title is going to be, and I actually want to display the L2 norm of the difference. So this is going to be the difference in grayscale images with the L2 norm of the difference of the grayscales of A, which I'm just going to abbreviate as norm GAD norm 2. That's going to be equal to, and to calculate the L2 norm, in case you already don't know, is going to be equal to num2 string of the norm. And since sometimes the types do not get sort of situated with some image conversions, it's sometimes easy to just do double when you want to do mathy type of stuff to images, or you want to sort of treat them as numerical matrices. And this is going to be the L2 norm of that matrix, and it's going to place that into the title of that last image. Because if GA1 and GA2 are the same image, then this difference is going to be the zero matrix, and hence its L2 norm should be equal to 0. You could also do the Frobenius norm and other norms if you're familiar with that, if that interpretation is a little bit more right for you. So let's just give this a run and let's sort of look at what those last matrices look like. So the first is going to be this grayscale transformation, and if you look at this quite closely, the left one looks a little bit more darker than the right hand side, so obviously these grayscale images are subtly different, but overall one may argue that they're practically the same image, and you can sort of do like, is there a significant difference between these two numerical matrices via statistical test in whatever way you would see appropriate. And then we look at, for example, the difference matrix. So if you look very, very closely, maybe you can see that there is a little bit more there is some difference between these images. In particular, the main difference is located on some of these plants, on the cute dog's nose, and in particular on her belly. And you might want to reference back to, for example, the color distributions of which ones are significantly intense in those regions, and then sort of see how that relates to the different grayscale transformations. But obviously the L2 norm is not equal to 0, so that difference is mainly located on her belly, nose, and some of the plants. So that is some of the basic color analysis that you can use for images, and those are some of the basics associated to image processing. I hope you enjoyed this video. There are plenty more image processing things that we will discuss in the future, but for now, that's all. Take care.